So Andrew just went through a presentation of looking at the Milky Way in the hydrogen line. I got the idea about 2 years ago. I wonder if you could use a backyard setup to actually detect the hydrogen line from extragalactic sources. So I went on this 2-year quest to try to detect M31. And last April, I succeeded. Not only getting M31, but actually M33 and possibly M101. That's still a little questionable. So today, what I'm going to go through is a tutorial on my methods. How did I do this? So in case anybody else wants to try it themselves. So let's see, this is not. So I'm just going to do it this way. All right. I guess I got it. Okay. So I'm going to go through a brief introduction here. Hydrogen line is an emission line of neutral atomic hydrogen. It's caused by the ground state electron flipping spin states. So it goes from a slightly higher energy when it's aligned with the nucleus spin state, and it's slightly lower energy when it's opposite. This transition is such a low energy difference that the emission wavelength is 21 centimeters. So it's in the radio frequency range. And Jan Oort, back in the early 20th century, thought this would be a very useful tool for mapping the structure of hydrogen in the Milky Way. This is my girlfriend and I at Green Bank last August, standing in front of Ewan and Purcell's actual antenna that was used to detect the hydrogen line for the first time. So this is the map of the Milky Way that Jan Oort produced. So you notice right in here, so you notice right in here, you got these cones of blank where there's no data. It's because even though we can detect hydrogen in this region, because the velocity is almost entirely tangential, you don't get any useful Doppler shift information. So it doesn't give you any spatial data. So it tells you, yeah, you have hydrogen, but you can't, there's no way to deduce structural information because there's no Doppler shift in these narrow cones around 0 and 180 degrees. Okay, so
just on that point, back up.
Yeah.
Okay, so if I'm using Doppler shift to do space, how do I know how far?
Well, so it was kind of explained in Andrew's previous presentation, but there's kind of a trigonometric thing that they do where it's like the termination of, it's like a tangential line of sight hits certain rings around the center.
So I get that, but somebody had to be the first one to make the correlation, because otherwise I'm just looking at Doppler shifted data.
Yeah, well,
maybe I have to go.
Oort was the one that came up with the methods, and some of his underlings, I think, Jan Oort was. Yeah, it was developed in like I think the 1950s, soon after they first discovered it. Or when you're observing extragalactic sources, particularly spiral galaxies, because you're looking at a source that is spinning, you're getting a proper motion radial velocity, but you're also getting the peaks the single emission line split into two because it's a spinning disk, and unless it's oriented completely flat from our perspective, we're getting some radial velocity blue shift and red shift from the spinning itself. And so you end up with a double peak with a flat in between. The more oblique the orientation is from our perspective, the wider the spectrum will be, the farther apart the two peaks will be. And I can actually show specific examples of this. I took survey data plots of integrated spectra of several galaxies, and I scaled the horizontal scale so that all the horizontal scales match in relative size, so that you can compare qualitatively how wide the spectrum is, and how as you get a more oblique angle, the spectrum is much wider, and as you get a more flat face-on view, the spectrum is almost a single peak because there's no Doppler shift, right? I actually have two methods that I'm going to go over. One is today I'm going to go over the drift scanning method with using a backyard setup with a small dish, and then tomorrow I'm going to do the follow-on where I'm actually going to show how we can use the 20-meter scope at Green Bank remotely accessing and actually do these observations using that. And I'm going to actually do an observation live from the presentation. So hopefully, if we can get it to work. So the first thing I start out with is planning the observation. And so, you gather the information on the coordinates and kind of the heliocentric proper radial velocity, so that you kind of know what frequency range you're actually looking at. And then the next thing you got to do is calculate what the local standard of rest or heliocentric correction is. Now, this is only important. So if you're just wanting to look at the spectrum and see the spectrum, you don't necessarily have to do this correction. But if you're wanting to actually compare your results against published survey data, you got to do a velocity correction to remove the orbital motion vector of the Earth around the sun from that data, because from your data, because the published data has that correction built into it. Now, if you're using, for instance, the lab survey data of the Milky Way sky survey to, like Edward Mole and I have figured out how to tease out of that data extragalactic sources and use that as an actual reference source. If you do that, you got to keep in mind that is using the local standard of rest. But if you're comparing against survey data where they were actually surveying the extragalactic sources directly, they're most likely going to be using the heliocentric correction, because that's typically done, I found out, with extragalactic observations in the professional world. So now those two numbers are usually very close. So you could use one or the other and you probably would be okay. But they can be as much as 10 kilometers a second different, because the difference between local standard of rest and heliocentric only subtracts the 30 meter per second rotation or orbital velocity of the Earth from the measurement. The local standard of rest removes that, but it also removes a fixed vector of about 10 meters per second. Then our entire solar system is moving through the local neighborhood. And so, depending on which direction you're looking, that can add an extra 10 kilometers per second of more error to your, or offset, I guess. I use this Green Bank site to do my calculation or to find the local standard of rest correction. Basically, just type in your date. You don't have to worry about time. That's only if you're trying to also correct for the rotation of the Earth, which is so tiny that in the realm of what we're doing, it doesn't even matter. It's like plus or minus a half a kilometer a second, which is in the noise. So I don't even worry about that. Then you put in your coordinates of your source that you're looking at, and it'll tell you what the correction is. So I use the Stellarium Planetarium app on my phone to plan my observations. I will set my location to where I'm actually at, and I will set the date and time for the times that I'm wanting to do my drift scan, and then I actually zoom my screen, my field of view, to match the half power beam width of my antenna, so that when and then I set it so that it's pointing due south or due north, depending on where what the elevation of the target is, right? And then I will basically step through the times until I find when the source just enters and leaves my field of view of my beam of my antenna, and then that tells me my timestamps on my data collection that are in beam, right? And so everything between this time and that time will be my main transit data. And then, but I start collecting at least an hour before that, and I keep collecting for an hour after that, so that I have plenty of pre and post transit data to build my calibration reference to. Because when you're doing extragalactic sources, we found that the most effective method for flattening your background and removing the local hydrogen signal as much as possible so that you can actually see the extragalactic source is to use fore and aft transit data as your calibration. So you're basically calibrating against empty sky very close to your object. And that works surprisingly well, believe it or not. So the next thing you got to do is you got to figure out what your center frequency needs to be based on the average velocity of the galaxy you're looking at. So you look at in your reference material, you find okay the average velocity of, in this case, the average velocity of M33 is around 180 kilometers per second, about blue shifted, so minus 180 kilometers per second. So you use this simplified. So this is not corrected for relativistic effects, but the velocities that we're talking about are so small that it works just fine, and it's a simple approximation. But basically, you plug in your hydrogen line frequency here. You got the speed of light in kilometers per second. You got your radial velocity of your object, and then that tells you what your observation center frequency should be to place that spectrum right in the center of your bandwidth of your receiver. Okay, and then you start collecting observation data. So this was my homemade 2.5 meter giant umbrella dish. It's made from plywood and dowels. My feed is actually a cake pan with a one wavelength circular loop feed, and my LNA bandpass filter is mounted right on the feed. And then I don't have any fancy mount. It's literally steel bolts attached to a plywood base, and I prop them up with bricks and paving stones, and I measure it with a ruler, and I do the math, and I say, okay, my elevation is correct. And I do my azimuth pointing eyeball. It's just, But my beam width, to be fair, my beam width is about 8 degrees on this dish. So as long as I get within plus or minus 1 degree, I'm pretty okay. Then I do use the AirSpy SDR Sharp software with the IF averaging plugin. So I set up my center frequency to match what my plan is. And then I use these settings. I found that this works well for doing extragalactic observations. I set my FFT resolution to 128 bins. I set my intermediate averaging to 1,000, and when I use a dynamic averaging of 7,659,000 counts, that gives me around 4 to 5 minutes of integration time per snapshot. So each of my data files have about 4 or 5 minutes of integrated time. Okay, then I connect up my SDR, my feed, my LNA, my bandpass filter, and then I press play and start recording. Launch the IF averaging, enable multiple save, and then yeah, I start collecting at least 30 minutes before my pre-transit start time to let the system stabilize before useful data is being collected. Then after you're done collecting your data, then you got to analyze it. So IF averaging plugin generates files with whatever file name you choose, and then it appends index number to the end of it, and they just go in order. And so I write down, I look at the file data to see what the timestamps are on those files, and then in my notebook, my observation plan, I figure out which file index numbers go in the pre-transit bucket, the main transit bucket, and the post-transit bucket. And then that's what I use then to choose which files I suck into I do my analysis in Excel. I just find that it's accessible, and it's fairly straightforward, and I don't know, it's just the way I chose to do it. I know that Edward Mole has built some Python scripts to do his analysis, but they're basically doing the same thing, just in a little more elegant way. But I dump my data files into a template that I built. I have pre-scan columns, main transit columns, and then post-scan columns. And each of the data files just literally contains a time date stamp, a number of counts in the integration. I've got frequencies and amplitudes. Those amplitudes are voltages because it's just literally a direct A to D conversion. So, and then I update my VLSR correction value in the template to whatever I found from the Green Bank site, and that basically recalculates all my velocities in the velocity column and corrects them for this so that my data will match the surveys that I'm trying to compare them to. Okay, so then I edit the pre, main, and post cells on the analysis sheet to point to the right range of cells on the raw data tab. And then, if necessary, I enter, so then I correct this center frequency to make my velocities line up with the velocity that's shown in the raw data sheet, so that everything lines up properly. And then I do a main divided by the average of pre and post. Because again, these are linear voltage amplitude values. And then I convert to dB using 20 log. And if I have multiple observation days, I just have multiple main over transit columns, and then I average all those together and convert to dB in this combined column. Then the last thing I do is I use a polynomial flattening function to correct the background drift, because it never stays totally flat, it moves around. And a lot of times I can get by with a first order, just a linear fit, but sometimes I do need a second order. I've never had to go into third, fourth, and fifth order. And what I do is I look at kind of background places where I know the spectrum is not that I'm looking for, and I try to flatten that part. And if you notice this little blip here, that's caused by the residual. It's at zero. Its velocity is 0 kilometers per second. That's the residual Milky Way signal that the calibration reference data couldn't quite remove, because if you think about it, the strength and shape of the hydrogen line signal from the Milky Way in slightly different parts of the sky is not going to be exactly the same. That's why I try to keep my calibration reference points as close to the main transit as possible, because it reduces the difference and makes this smaller, but it's always there. I find it's actually useful to make sure that I actually did my LSR correction properly, because if I did it right, this should be at 0. If I didn't do it right, it's going to be way off. It's going to be off at like plus or minus 30. And then this little part here, that is actually M33. That's in this particular case. And there's my M33. The top is data that I pulled in from, I believe it was from the Things survey that was actually done at the BLA. And then this is my data. And I actually tattooed my first detection on my arm. So. And there's a call sign here too. That's Jean-Jacques Montclair's call sign, because about 6 months after I succeeded, he passed away. He was in his 80s. And so I thought, that would be kind of a nice tribute to him, because his paper was what really inspired me that this is possible. He was the first one to show that you could do it with a 3-meter dish. And so anyway, that's all I have for today.